In this video and in the subsequent videos, I'll be discussing about two important concepts used in the statistical modeling or predictive modeling. One is the weight of evidence, or in short known as WOE, and the information value. In this video and in the subsequent video, we are going to learn the following things. First, we were going to learn what are weight of evidence and information values. So we will learn the definitions, and then we will learn how to calculate the WA values and the information values of variables. And then we will learn how to use these concepts in order to build the models. So we will learn how to do variable reduction using information value, and then how to calculate the WOE and information value in SAS. And finally, we will learn how do we use the WOE concept in logistic regression modeling. So let us first learn what is weight of evidence, or WOE. So weight of evidence is a variable transformation technique. We do variable transformation of the independent variables, and the concept is actually taken from the information theory. So what variable transformation do we do, and why do we do it? What are the uses? Well, we do variable transformation the purpose of grouping. So that's the first thing. For the purpose of variable selection or variable reduction, if you have too many variables, to reduce to an important set of variables, we also use this transformation, and to find out the predictive power of the variables, or the predictive strength of the variables. So what transformation do we do with the variables, we will discuss later on in this video. So first let's learn the definitions. So the weight of evidence is some kind of a measure of the strength or the ability of the variables to separate two categories of the dependent variable. So I'll just repeat. So it measures the strength or ability of variables, mostly independent variables, to separate two categories of dependent variable. So for example, and it will be more clear if you take an example. For example, let's say the dependent variable with us is the category of customers. So a customer could be a good customer or a bad customer. Okay, like in a logistic regression, if it's a good customer, then we assign it as a 0, and it's a bad customer, we assign it as 1. And we have got two independent variables. One is age, and the other one is income. Now we want to build a model to predict a good customer or bad customer, or the customer type based on age and income. So we will have two logistic regression model, or any binary model. Customer type and the independent variable is income, and then customer type and the independent variable is now age. Now when the independent variable is income, the model is able to predict 70% of the customers correctly. So good, bad customers. So good is assigned as good and bad is assigned as bad at a cutoff value. Okay, say for the cutoff value is 0.5, the probability value, and at this cutoff value the predictive power of the model is 70%, or it is able to predict 70% of the customer correctly. When you use age as the only independent variable in the model, keeping the dependent variable same, at the same cutoff, let's say that it's able to predict 60% of the customers correctly. What we can say is that the ability of the independent variable income to separate good and bad is more than the independent variable age. Hence the weight that we can give to the variable income will be much more than the weight that we can give to the variable age when we use these two variables in the same model. And that is why the name of the term weight of evidence. So the evidence is that it is able to separate two different categories. And what should be the weight? The more the weight, the better is the variable, or more powerful is the variable. So what is the definition of the weight of evidence? It's simple. It's the logarithm of the percentage of good by the percentage of bad, where the small n is the sample count or the count of a particular group, and the capital N is the total count of good or bad. Okay, and also sometimes we multiply with 100. So many people use it for scaling purposes, but it doesn't make a much difference to the interpretation of the WOE values and its uses in the model. So you can use either of this formula, this one or this one. Just to explain you a little more in detail. So weight of evidence is logarithm of the percentage of good. So small n by capital N. Small n is the number of good customer in a particular bean, and capital is the number of customer in a total number of customer. Similarly, number of customer denoted as bad in a particular bean, and total number of customer. So what is this bean, or what is this grouping? We will talk about this grouping later on when we take an example and how we do the grouping and all. So that I know things will be very clear at that point of time. So this is the formula that we are going to use. So how do we calculate the weight of evidence? It's pretty simple. We will use the same formula that we saw just now. So here is an example. We have got the variable age and the corresponding good bad indicator or the dependent variable. So I've got the dependent variable which is customer type, good and bad, and the independent variable age. Now let us calculate the weight of evidence or the WOE values for this variable. Now we have got how many observations? 10 to 12 observations. In a real life scenario, you will have like thousands or hundreds of or even more observations in place. So the calculation that I am going to do here is actually not possible to do manually. One has to write codes for that, but I have taken a very simple example to ensure that we understand the concept of WOE properly and be able to calculate it manually. Although for large dataset one has to write an automated code. So the first thing that we will do is we will group the variable age into different age groups. So the first age group that we will have in the age group is the less than or equal to age 25. So that's the first group. And how many observations come under that group? First observation, which is 24, that comes under this, and then the second one also 25, and then this one as well, and the last one. So there are 4 observations falling in that category, less than or equal to age 25. The next age group is 25 to 30. And then we have observations like 28 and then 26. So these 2 observations are there in that particular age group. And the last age group is the greater than 30. Now we will also calculate the number of bads and the number of goods. Now remember the formula. The formula is the logarithm of percentage of good by percentage of bad. So to calculate percentage, we need to calculate the number of goods and bads in each categories. Okay, so below 25, so the first age group we have 2 bads and 3 goods, and the total is 5. Within 25 to 30 we have 1 bad and 2 goods. Okay, so how do we know bad and good? I haven't yet told you. Well, if a customer, if the good bad customer takes a value of 1, then it's a bad customer, and if it takes a value of 0, then it's a good customer. Okay, so that's the definition of good and bad, the customer type. Similarly, greater than 30, we have got 1 bad customer and 3 good customers, and the total is 4. It's just additional. And the total number of bads in our entire sample is 4. So in the total you have 4, and total number of goods is 8. Now we will compute what is the good percentage and the bad percentage. The first is bad percentage. So bad percentage in the age group of less than 25, less than equal to 25 is 2 by 4. So this one 2 by total. That means number of bats in that age group divided by the total number of bats in the sample. Okay, and that comes out to be 0.5. Then for the next age group between 25 to 30, then it's going to be 1. So only one bat customer is there, and the total number of bats in the sample is 4. So 1 by 4, which is equal to 25. 0.25. Then greater than 30 age group, 1 bat customer, and then the total is 4, so 0.25. Similarly, we can do the same thing for percentage of good. We have got 3 goods in the age group of less than equal to 25, and the total number of goods in the sample is 8. So 3 by 8 is 0.375. Similarly, for the next age group, it's 2 by 8, 0.25, and for the last age group, which is greater than 30, we have got 3 goods, and the total number of goods is 8. So 3 by 8 is 0.375. Now we have bad percentage and the good percentage. Now remember the formula. It's the logarithm of percentage of good by percentage of bad, and we have got percentage of good and bad. So what we can do is that finally we can just put these values in this formula, logarithm of 0.375 by 0.5. So first WOE value for the age group less than equal to 25. So and we get this value minus 0.124. Okay. For the next variable, for the next age group, the percentage will be 0.25 by 0.25, because the good percentage and the bad percentage in this age group is exactly same, 0.25 and 0.25. Doesn't happen though very often, but this is a special case. So that becomes logarithm of 1, and the WOE value is 0. And for the last age group, we have the WOE value as 0.17. So that's the way we have got a transformed variable now, which is the age underscore WOE, or a new variable, totally a transformed variables. Now initially our variable was like this, age, and having values like 24, 25, 28, and now we have got a totally different variable, age underscore WOE, which is transformed variables. Instead of having 12 observations, we have now only 3 observations. So we have grouped the variable into 3 different categories, or 3 different discrete values. So we have grouped the variables. And why do we do the grouping? We will talk about in a separate video, in a subsequent video in this playlist. So these are the values that we are going to use for the modeling purpose instead of using the original variables. So this is the original variable, where this is the transformed variable, age underscore WOE. So in place of these values, for example, when the age is less than equal to 25, one has to use the values minus 0.124. So we have just replaced the value as 0.124, minus 0.124. Similarly, for the next observations, the age is 25. We have replaced with the same WOE value, minus 0.1249. The next one is 28. So we have replaced it as 0, because the WOE value for the age group 25 to 30 is 0. So that's the way we have transformed the variables and replaced the values of the variables and calling it in a different name, age underscore WOE. So this is going to be our new data set, which we are going to use for modeling purpose, and we will see in a video that how this grouping actually helps us in the predictive modeling. In the next video, I'll talk about what is information value. So watch the video on information value.